Yes, I hope you attempted at the problem set, and I think some people did, and some people even finished it, so that's good. Yeah, but you still have some time, so because we extended the deadline until next Thursday. So if you're busy or something here, I'll post the second one. I think there will be 3 in total for this course. Yeah. Okay, so we still looking at ergodic theorems. And today we're gonna see basically the proof of all of them, because we proved the hardest one, the subadditive ergodic theorem, and then from there you get the other ones basically. And so let's recall once again the setup. So we have a space which we call X, but eventually we're going to call it omega when we apply to random walks. And T is a measure preserving transformation. So this is a measure preserving system. And yeah, so we have two types of settings. So we have F from X to R is an observable, so something you can use to test your system. And so and then we have this notion of Birkhoff sum. So we have a notion SNF, which is the sum of F composed with T to the I from I equals 0 to N minus 1. And so Birkhoff theorem says the following. So this is the Birkhoff ergodic theorem. Is that almost surely the average, the Birkhoff sum divided by n converges to an invariant function. So for all there exists some function f bar also in L1. So if f is in L1 of xp, there exists f in L1 also, f bar in F1 with f bar composed with t equals f, such that S and f over n computed at x converges to f bar of x for almost every starting value of x, for almost every x. So remember, this is the additive version, because here we're taking the average by adding the value of the function along the orbit. And the strongest version is the Kingman ergodic theorem, so which is the following. So recall that you have a subadditive co-cycle, a subadditive co-cycle is what? Is a function a from n times x to r. So here, instead of looking at for each n, we do the average along the orbit. In principle, we can have a different function for each time. So this n is like time. And it's subadditive, such that a n x is less or equal than, sorry, a n plus mx, function of times n plus m, is less or equal than a n x plus a m t n x. This is for every m n in z in n, and for every x in x. And recall, as I said before, that the easiest example is to set a and x to be really this s and f of x. This would be really an example where instead of the less or equal, you have equality. So, and the assumption is quite similar. So the only difference is basically that you have less or equal instead of equal. And so here the theorem is due to Kingman. Again, this is a bit later in the early 60s or even maybe very late 50s, something like this. That is, let if A is a subadditive co-cycle, over a measure preserving system. So X is measure preserving system. So this is our measure preserving system. And okay, we have two conditions. The most important one is an. For every an as a function of x is in L1 of xp. So it's the integrability condition. And in some cases, it's enough to check A1. I mean, there's a little bit because of the special, for instance, if A is positive, it's enough to check it for n equals 1, because by induction and using this, so an upper bound you can get from this by induction. And the second one is, okay, some non-degeneracy, if A is negative, well, in principle, you could have that this average goes to negative infinity. So to exclude that, yeah, so to exclude that, we just say that the infimum over n of 1 over n, the integral of an x dpx is not negative infinity. But for us, mostly our A will be non-negative, so it's not the biggest deal. So then it's a similar thing. There exists some function A bar in L1 with A bar composed with t equals A bar, such that the limit as n goes to infinity of A n x divided by n is A bar for almost every x in x. So you see that it's really very, very similar. Okay, so now we are finally ready to give a proof. So we're basically going to give a proof of Kingman's theorem. Are there any questions about the statements or anything? Cocycle, yeah, I mean, so cocycle usually has equality here, actually. So, yeah, but there is a cohomology theory of group actions. So, in fact, yeah, yeah, so basically, yeah, the basic idea is that if you have a function, you can define its boundaries as f minus f composed with t, if you have a dynamical system. And yes, and basically, yeah, basically you have a boundary operation, and if you have this that satisfies equality here, yeah, you do have something that is trivial boundary. So there is a cohomological interpretation of this, which yeah. Okay, so but less or equal is for subadditive, then it's not quite. It's because you have less or equal. Yeah, but there's other objects in geometry that satisfies cocycle property. For instance, the Boltzmann function would be the most common one that you guys probably heard of. Yeah. So the proof of Kingman's theorem there will take us all the lecture today, I think, because it's a bit long, not too complicated, but well, definitely not trivial. So okay, so let's start with the first thing about subadditivity is the famous Feketa's lemma. I'm sure many people had the same idea. For some reason, Feketa's name is attached to this. It's probably Hungarian combinatorialist, something like this. So, but anyways, so Feketa's lemma is just about numbers. It's not about functions. It's the easiest way. And so is the following. So you start with Vn as subadditive sequence of real numbers. So what does it mean? It means that V of n plus m is less or equal than Vn plus Vm. Okay. And then if that's the case, there is a limit here. The average converges to a limit. Then the limit as n goes to infinity of 1 over n times Vn exists, and it's equal to the infimum over n of 1 over n Vn. So the average keeps going down. You wait, but it gets to a limit. But however, this limit could be in R, or it could be negative infinity. So if you allow for that, yeah. Okay. So what's the proof? This. Yeah. So this is maybe an exercise that we've seen in other courses, maybe in analysis courses and stuff. So how do we start? So we say we take some epsilon, and okay, we know that this is the infimum. So there exists some m such that if you do Vm over m, this is going to be less or equal than the infimum plus epsilon. Some point you have to get close to the infimum. And the trick now, the main trick is to do Euclidean division here, the Euclidean algorithm, using the subadditivity over and over again. So what happens is the following. So if you, for each n, can be written as the follow, as like this, n equals kn times m. So we do the division by big M plus Rn. So this is from Rn to M. Anyway, I have lecture notes about this, so I will post them. This part is not yet posted, I think, but I'll add. So okay, so we did a Euclidean division like that, and then we use this to combined with the subadditivity to get an estimate So how does that work? Well, it works like this, that if you do Vn, this is V, Kn, M plus Rn. And then by subadditivity, every time we can subtract Kn m times. So this is less than m times V Kn plus Vrn. Right? Okay. And now we divide by n. So we have that the infimum over m of Vm over m is less or equal than 1 over n Vn, of course, which is less or equal than 1 over n times m Vkn plus Vrn. Okay. Okay, and now yes. Now how do we choose Vm here? And what's the other thing? The other thing that you want to observe is that Kn over n converges to what? Let's think about it, right? So we write n equals Kn m plus Rn. So if we want to know the ratio between n and Kn, what is that? Yeah, exactly. Kn over n is 1 over m, because Kn over n times m plus this remainder term equals 1, and then this remainder term goes to 0. So this one goes to indeed 1 over m. Okay. So, oh, sorry, I did the opposite here. Sorry, that was kn here and m here. Of course, it's this the same division. We can do the other way, like that. Okay, yeah, now it makes more sense because kn over n goes to 1 over m. Okay. Yeah, so this one. Yeah, so let's think about that. So what else? So what about VRN divided by n? Where does that go? Yeah, it goes to 0 because Rn is only, there's finitely many choices for that between 0 and big. Yeah, so we're fixing the big M. So this one in the end is Vm over m. And there's some epsilon that comes from this limit and some other epsilon that comes from this limit. So it's like that for n large, for n large. Okay, and then we're done basically because this one is less. Well, we chose big M for like that. So this one is less or equal than the infimum of Vm over m plus, well, another epsilon. So 2 epsilon. So you see, what did we show? We showed that given epsilon, for n large, Vn over n is sandwiched between the infimum of Vm over m and the infimum plus 2 epsilon. So from this, we get that the limit as n goes to infinity of Vn over n equals the infimum. Okay, so that's kind of the first lemma, which again, it's sort of the basic principle of subadditivity. That's whenever you have subadditivity, you have some variation on this argument, basically. Are there any questions about this argument? Okay, so now we need another lemma, which is of different flavor. This is a lemma apparently due to Wies, which is called lemma on leaders. This is the nickname. So is the following. So we define the following. So you start with a sequence of numbers. Let C0, C1, Cn minus 1 be a sequence of real numbers. And we call some elements of such sequence leaders as follows. So we call the term Cu a leader if at least one of Cu or Cu plus 1 or all the sums from Cu to the end. So Cu plus 1 all the way plus Cn minus 1 is negative. So yeah, what happens? How do we make sense of this definition? So suppose it's 0, 1, 2, 3. This is our n. And suppose here we are plotting the sum. Let's plot SU, which is C0 all the way to CU minus 1. So let's plot Sn here. So what does it mean that it's a leader? Well, so if you're plotting the sum starting from the beginning, it's a leader, meaning that it means that afterwards, at least once afterwards, you go below it. So that's one interpretation of why one calls it a leader. So I mean, you start at 0, for instance. So depending, C0 could be a positive or negative. Let's say it's positive. And then you see, maybe you still go up, and then maybe you go down like this. So you see, so this is just C0, this is C0 plus C1, this is C0 plus C1 plus C2. So which one is a leader here? Well, this one is not a leader because it goes up again. But this one, let's see, yeah, this one is a leader because eventually it goes down. And this one too, because, okay, not immediately, but after 2 steps, it goes below it. So that's the sense of this definition. And the lemma says the following: then the sum of the leaders is non-positive. Could be 0, but it's never positive. Okay, so yeah, this is also somewhat simple lemma, even though kind of ingenious. So okay, so let's see the proof. Maybe we can crowdsource this proof. It's not that complicated. So let's see. So what do you suggest? How would you proceed in such a proof? Yeah, induction. Induction is a good idea. Okay, let's see. So induction, of course, the only induction which makes sense is induction on the length of the sequence. Okay. So since Vivian picked induction, she can start with the base case, which is the easy one. So what's the base case? Yeah, you have one element in your C0. So is C0 a leader or not? Well, C0 is a leader if and only if it's negative, right? It's a leader if C0 is negative. So clearly, the sum of all the leaders, well, if there's no leaders, it's 0. And if C0 is a leader, it's negative, so we're good. So someone braver can do the inductive step. Let's see. Anyone wants to give it a try? So we start with C0, C1, Cn minus 2, Cn. Right? So what do we do with this sequence? What's the trick? How do we reduce to the previous one? Yeah, here the Yeah. Yeah, I think that the way that they suggest that is we sort of remove C0, but yeah, maybe you can also do that. So let's see. So there's two cases. So there's a case one is that C0 is a leader. And the case two is that C0 is not a leader. So let's see what happens. If C0 is a leader, what are the other leads? Of course, yeah, then we look at this other sequence. So then what are the leaders? That's right. So C0 is a leader, so we already know that C0 is negative. Otherwise, it wouldn't be. No, we don't know that in this case, right? No, sorry. But the leaders of the other subsequence, yeah, right. So the leader, sorry. So the leaders, yeah. So the leaders of the whole subsequence are, yeah, the leaders of C0, Cn minus 1 are C0 union the leaders of the subsequence. This one we definitely know. Because testing whether someone is leader only has to do with the tail of the sequence. Okay. So now what does it mean that C0 is leader? Not quite that itself is negative, but at some point some sum is negative. So in fact, there exists K such that C0 plus C K minus 1 is negative. Okay. So how do we conclude from here? So this means, so let's, in fact, we have to change slightly this. So you see, so if these are leaders, so C0 is leader, there exists one for which this sum is negative. Now we want to say that the other terms are in between 0 and K are also leaders. Yeah, I mean, okay. No, we're done. Yeah. Yeah, if C0 is non-negative, yeah, how do we do? Yeah.
Then like the rest of it has to come to a negative number. So I mean there's a C1 has to be a leader.
Right. If C0 is negative, then the rest of it has to be negative, right? Yeah, that's
And I guess basically it's like stuff about that.
Yeah, the claim was that in this case, every CI with I less than K is also a leader. Let's see, is that true?
It should be the largest one, so that's C0 to
Yeah, we have to. We have the ability to pick K, right?
Because if you were to do that and factor K, you cannot have a leader. It's negative and you cannot.
Right.
Because you know that the since C0 is the leader, that means that the sum of the rest of the leaders has to be less or like greater than the negative of C0, right? Otherwise C0 would be a leader. So then, and you know that the sum of the rest of the leaders is negative. That means when you sum the rest of the leaders plus C0, you still get a negative number. Isn't that the solving?
Yeah. So you want to go to the two cases: either C0 is negative or C0 is not, right? Or you don't need that either. Okay. So how do you do it again?
So we know that the the meters of C1 to n-1 is first the absolute value of that is less than C0. By definition, C0 being the leader.
So let's.
That's for the existing case.
Yeah.
You don't know the comparison.
So let's see. So C0. Yeah, I think what you said before to distinguish whether C0 is positive or not, maybe that's not a bad idea. Because, right, I mean, if C0 is negative, then it's okay, right? Because the leaders of, again, C0 Cn-1 is C0 union the leaders of C1 Cn-1. And we know that the sum of those is negative, is non-positive, and this one is negative. This is fine. Okay, so now the question is, what happens if C0 is positive, maybe even, yeah, right, I mean, yeah, if C0 is positive, as you said before, like, yeah, so the sum of the other ones.
We want the case such as like C0 plus CK minus 1 is less than 0. And also like all the sum before is bigger than 0. So we want the case to be the first one.
The first one, right? Yeah. So C0 plus CK minus 2 is bigger than 0. Okay.
And also all the previous sum are bigger than
Yeah,
0.
yeah.
And then I think you can come up with that.
Okay. So how do we do that? Yeah. So yeah. So let's say K the minimum. Okay, so how do we conclude from here?
The non-leaders have to be positive.
Say it again.
Oh, like the sum from C0 to say CK-1 is greater or equal to the, sorry, less or, oh, it's less or equal to, sorry, greater or equal to the sum of all leaders between 0 and 1.
So what? So you want to take K minus 1? And then what?
This is greater or equal to
Either between 0 and k minus 1. Okay.
So the right side is also.
But you have positive here. So
Yeah, but the left hand side is straight forward. So we also have the right side.
I don't understand. Sorry. Wait. Yes.
So if C0 is greater than 0, then you consider C1. C1 must be a leader.
Yes.
And then you discuss C1. So if C1 is positive, then you conclude C2 is also a leader. Then it just changes wrong. And if C1 is less than 0, then you know C0 plus C1 is positive. Must be positive because K is minimum. And if C0 plus C1 is positive, then you know C2 is also a leader.
Mhm.
It's kind of like there's a sub-induction.
Yeah. No, I think it's only a matter of writing in the right way. So how do you? So how? Yeah. So
Now try to argue C1 is a leader.
right.
And then you discuss whether C1 is positive or negative.
Yeah. But how is the easiest way to write this? You want to write it? No. I don't know. What's going
I
on?
think the left-hand side is greater than 0. Sorry, 0 is greater than the left-hand side based on that above.
Yeah.
I don't know where you go from there.
So the right hand side is the sum of leaders between 0 and k minus 1 that's less than 0. And then we do induction, apply the induction plus it is all remaining. After k.
Yeah.
So like there, it says there exists cases that like we know that the sum of 0 to k minus 1 that's greater. Sorry, that's less than 0. You can write a 0 less than on the left, far left.
Okay, very good. So how about you guys do it? I don't know. Like, this is a kind of proof that when you read it, it makes sense. But then in front of the board, you get confused. So yeah, do you want to write it? Does anybody want to write it? This is the easy thing.
So can I?
Sure.
From that hypothesis, like 0 is greater than this.
So why is 0 greater than that?
Oh, this is because this.
Yeah.
The
Yes.
definition of
Yes.
So I have this being negative.
No, but that's not enough because there is like some elements might be greater than the entire like sequence, but not greater than that subsequence.
Oh, here I mean the leader in the entire sequence.
Wait, so
Because as long as it is a non-leader, that means all these are constant. So the element itself is positive. So by removing those non-leaders, I get a more negative.
No, it all makes sense, but honestly, I'm completely confused. I cannot read any inequality. So let's keep going. So for the case equals 2 is easy, is the easier case, which is C0 is not leader. Yeah, I mean, C0 is not leader, then the leaders are only the last ones, right? And so the sum of those is less than 0. Okay, so let's let's think about it over the break. Let's keep going. So now let's keep going. So what's the next lemma? So the next lemma is you start with the subadditive cocycle. And then we look at the functions f of x, which is the lim sup of an x over n, and then gx is the limit. And the claim is that, that these functions are almost everywhere invariant. So F composed with T equals F almost surely, and J composed with T equals G almost surely. Okay, so in order to do that, well, we just need to look at the subadditivity question. Subadditivity. So an of x is what? Is bigger than, yeah, an of tx is bigger than an plus 1 x minus a1 x. And then we take the lim sup, so we divide by n here. And we take the lim sup. So the lim sup over n of a and tx over n is bigger than what? Well, it's bigger than the lim sup of this. And in order for this one, we can multiply and divide by n. So you get by n, and then you do minus a1x over n. Okay? So what happens here? So this get, sorry, n, sorry, you had n, 1 plus 1, plus 1. So this one is the lim sup over n of n plus 1 x over n plus 1, and plus 1 over n is going to 1. And then, well, the lim sup of this goes to 0. So this one gives you f composed with t, because this is the lim sup over tx, is bigger than f. And so similarly, we get g composed with t is bigger than g. Okay. So however, what else do we know? We know that the t is measure preserving. So here's another thing to check, is that f is integrable. It's also not completely trivial, but if so, what do we have? We have that the integral of f composed with t in dp is bigger than the integral of f in dp. And now, what else do we have? Well, we know by invariance that this is the integral of f in dp. So these two functions are, one is bigger than the other, but the integrals are the same. So they must be the same almost surely. F composed with t almost surely. And they're the same. And also same, g equals g composed with t almost surely for this. Okay. Are there any questions about this one? Yeah, the only slightly subtle point to check is that f is integrable, and this will follow from the integrability of the cocycle and the cocycle property. But yeah, there will be maybe a homework exercise to check this. Okay, so before we take a break, we can also state the main lemma that we're going to need, which is the following. Is the maximal ergodic inequality proposition. It's called the maximal inequality, which is somewhat the key to every ergodic theorem. And it's the following. So you start with A and X, a subadditive co-cycle. And let B to be the point such that the limit of 1 over n A and X is less than 0. So you see this limit. Now, we don't know the limit exists, but we can take the limit. And we check that the limit and the lim sup are invariant already. So of course, the whole thing is to show that both the limit and basically the limit and the lim sup are the same. And so, in fact, what we're going to show eventually is that the set where the limit is different from lim sup has measure 0. Okay, so the maximal inequality is the following. Then we have that if we do the integral, so if we do the limit as n goes to infinity of 1 over n, the integral over b of a and x dpx, this is less or equal to 0. So you see, we're taking this co-cycle and we're integrating it over the set where the limit is negative. And the non-trivial statement is that the integral, the average of the integral also is non-positive. And so in fact, to do this, we use this infamous lemma on leaders that we got stuck on earlier. So anyways, so this one has a few steps. I don't know. Well, maybe we can start. We'll take a break. Okay, so the first remark is the following. You want to note that T inverse of B equals B. So why is that? Or at least up to measure 0. Yeah, which technically would mean that the probability of the symmetric difference is 0. Yeah. Yeah. Yeah, because the limit is invariant by T. And so the set where the limit is negative also has to be invariant by T. That's exactly right. Okay, and now we construct another sequence of sets, AN, which is like that. So this is the set of X such that the infimum for 1 less than K less than N of A Kx is less than 0. Okay? And we have another set, psi n, which is the set of X such that the infimum of 1 less than K less than N, A and X minus A n minus K P Kx, that is less than 0. So we see we have the two parts of the co-cycle equation. You have this one and this one. And remember, what is the co-cycle equation telling us? Well, the co-cycle equation is telling us that AN X is less or equal than AKX plus A N minus K PKX, right? So from this on, what do we know? We know that we can flip this on the other side. So A N X minus A N minus K PKX is less or equal than AKX. Okay, and so what do we know? We know that if the infimum of this is less than 0, well, this one is less than 0 too. So if the infimum is less than 0, then this one is also less than 0. So this tells us that the equation is an is contained inside n. Okay, very good. So now what else do we have? Well, if you compare an and an plus 1, what do we have? Well, we have, so this is the infimum over the first n, and this is the infimum over the first n plus 1. So if the infimum is that you can reach in the first n is going to be negative, then of course, if you take the infimum on n plus 1, this is also going to be, okay? And the other thing is that B, which is, remember, B is the set where the limit of an over n is negative. Well, this has to be contained in the union of the an. Why is that? Because if you see, this means that an, the limit, yeah, so we mean that the limit of this is negative. So if the limit of this is negative, it means that at some point the inf has to be negative. Okay, so this is all good. So yeah. Okay, and also we need another notation. Sorry, this proof is a bit full of notation. Vn of x is the difference between an x minus an minus 1 tx. Okay? And so now, because we want to do a telescoping argument. So what do we have? We have an x minus an minus k tkx. And this turns out to be bn of x plus bn minus 1 tx, so forth, plus bn minus k plus 1 tk minus 1 x. So you can just telescope using this. So this is a little bit like a Birkhoff sum. So that's the issue. Yeah, and what else do we know? We know that a0x by definition is 0. And so we know that if we plug in k equals n, we have that n and x is the sum of bn minus k pkx, where k is between 0 and n minus 1. No, this would be equality, I think, because we define this to be the difference. So at each step, right? So you take the difference between different steps and you sum them and you get the difference between the n minus k and n. Right. Okay. So what do we claim here? Well, so now I think we need to take so the claim is that tkx belongs to psi n minus k. Let's see why is that the case. So psi n is that the infimum of the b of this one yeah, means that the infimum of this is negative. So we want to, yeah, I think we want to assume that maybe X is in B or something like that. So because what do we want to say? Yeah, eventually we want to say that there exists J and K, and such that K is less than J, less than n minus 1, such that Bn minus K times Tk x plus Bn minus J Tj x is negative. And then the idea is to apply the lemma on leaders. So I think the idea is that if X is in B, so the limit of the ratio is negative, yeah, there has to be a K and J for which this is true. Okay, maybe it's good time to take a break before we finish this proof. But yeah, so let's yeah. In the meantime, we can think of this stuff. Okay, let's see. Yeah, let's take a 10 minutes break then. Yes. Okay, so let's go back to the lemma about leaders. So let's finish that. So remember, by induction, we have a sequence C0, Cn minus 1. And we want to show that the sum of the leaders is non-negative. And so it goes like this. So suppose, so the case one was if C0 is a leader, then it's very simple, but as usual, you have to do it one way. It's just like this. You let K be, so at some point there is sum gets negative, so you get K to be the minimum of the H such that C0 plus C H maybe minus 1. Yeah, the question is CH or CH minus 1. Let's say H is negative, so this must exist because this is a leader. But since this is a minimum, by minimum, well, all the previous one are positive. So we have C0 is positive, C0 plus C1 is positive, up to C0 plus C H minus 1 is positive. And the next one is negative. So now the claim, which I was making earlier, is correct. But yeah, the only thing is to take the minimum. So the claim is that indeed Ci for any I less than K is a leader. And the proof is indeed very simple. So what do we need to show? What do we do? Well, we use this guy. So we say that we want to do Ci all the way plus Ck. So this is less than minus the sum from C0 plus Ci minus 1. Because of this, because of step K is negative. And now the other thing is that all the previous one are positive. So this is negative of a positive 1. So it's negative. So it might have well been what 5 of you guys were trying to tell me, but I was completely, you cannot reason in front of the board. You have to do all the reasoning ahead of time. So anyways, that's it. So then that's enough because, right? So let me just say it. That's enough because what else? Yeah, so by induction, right? So by induction, yeah, the sum over, yeah, let's call it the sum of the leaders of Ck plus 1, Cn minus 1, and this we know is negative. And then we add all of those guys are leaders. But we know exactly that this one is negative by this assumption here. And this one was non-positive, so okay, good. Any more comments about this? We're good? Was it different than your proof, or is it the same proof? Okay, good. So let's okay, so let's keep going. So okay, so now we have to apply this lemma about leaders. So how do we apply it? So yeah, so remember, so we came up with this way of writing A and X as this sum of the various increments. Now, what do we need to do? So the claim is that if X is in B, yeah, so if X is in B, so what does it mean that X is in B? It means that an over n, the limit is negative, right? So at some point, this sum has to be negative, right? And so remember that we defined, so this is literally, yeah, so these are the partial sums of this sum. So yeah, so the upshot is that if X is in B, then for some k, so there exists some k less than n, such k that for some k, you have to have the tkx is in psi n minus k. Yeah, you have to keep track of the various indices, but that's what it is. And so if you rewrite this, literally what it means that there exist two indices k and j, such that if you do a part of the sum, part of the sum has to be negative. So that's the point. So now we do apply the famous lemma about leaders. So what do we do here? Well, we conclude the following. We conclude that, so this is literally means that, you see, this time k is a leader, because if you look at this sequence, the sum of the tail of the sequence is negative. There is some, so by the lemma on leaders, we get the following. You get the sum from 0 less than k less than n minus 1 of tk x is in psi n minus k. If that's the case, you get b n minus k tkx. This is less or equal than 0. Because you see here, you're summing over this condition amounts to saying that this is a leader. So we're summing over all k such that it's a leader, and the sum is less or equal than 0. And now we integrate that, and we get the following. So we get that, so by integrate, you get the sum from 0 less than k less than n minus 1 of the integral of b intersect t minus k psi n minus k of b n minus k dkx dpx. Well, this has to be less or equal to 0. Again, we're intersecting with b because exactly we are using the fact that x is b, is in b tells you that this sum at some point has to be negative. And so we get this thing here. Okay, and then from here it's kind of just doing manipulation that we should be able to do. So the first thing to notice is, again, using the invariance by t. So using the t invariance. Okay, so using the t invariance, what happens is that we can remove this. We can remove this. Here we should apply t, but we know that t inverse of b is the same as b. So we might as well think of it like that, and then we can remove it. So this is just the sum, like that, of b intersect psi n minus k of b n minus k of x dpx. Okay, very nice. So, right, it's tk invariance. Yeah, of course. I mean, if it's t invariance, right, okay. Yeah, exactly. Yeah, but we're taking, for each the sum, so for each of them. Okay. So we're in a quite good shape. So now we change n minus k with I. So we let I equals n minus k. Okay, so this just is the sum from I equals 1 to n of the integral of b intersect psi I of bi of x dpx. And then what? Yeah, and then we go back to the original thing that we want to prove, and we apply this. So what do we want to prove? We want to prove something about 1 over n, the integral over b of a and x dpx. We want to prove this is negative. And so we split it in 2 parts. So we remember we had the set psi I plus psi n that were defined. So we have to split it in 2 parts. So one is the sum over b intersect psi I of bix dpx. And the other is 1 over n sum I equals I to n, the integral of b not in psi I. Okay, and then we use the following fact that this integral we showed is non-positive, less or equal to 0. Right. So we take that. So the only thing, so we know this one is negative. So the only thing that matters is this one. And then we're just going to say eventually that this is somewhat negligible. So now, why is this negligible? Well, again, we have to think about it. We recall that we had that AI, as we defined before, is inside psi I. And so we know that b minus psi I is less than b minus AI. Let's just contain it. Right. So remember, we also said that B is contained in the union of the ANs. So in the end, it's like whenever what's as n gets larger and larger, AN more or less covers B, and so this set becomes very, very small. So we just have to show that the set, this integral over this set, which is kind of small, a small measure, goes to 0. And of course, this follows for some integrability condition. So let's see. So yeah, so this is just by integrability condition. So what else do we know? We know that bi of x is less than a1 of x is less than a plus 1 of x, which is the max between 0 and a1 of x. This definition. And again, B is inside the union. And so we just estimate this using a1 basically. So this is less or equal. This thing is less or equal than 1 over n, the sum from I equals 1 to n of the integral over b minus ai. So because we can take this as bigger. We take only the positive part, it doesn't matter. Right. So this is just the integrability. So these bi's are controlled by a. A is integrable. So here we're taking the integral of this, which is, this is bounded by this function that is integrable. And then the measure of this set goes to 0 because of this, the limit. So you're taking an integrable function over a set of measure 0, small measure that gets closer and closer to 0, and so this one goes to 0. Okay, so this shows the maximal inequality, which in a way is the most technical part of the proof. And now we have to apply this to Kingman's theorem and to Birkhoff's theorem. It's actually not enormously complicated. So, okay. So now we can do the proof. Also, a corollary of the maximal inequality is the following. That if we define b tilde, so instead of taking the limit to be less than 0, we can put another parameter. So this is a set of x, such that the limit of an x over x is instead of less than 0, instead of less than lambda. Okay. Then what do? We take the limit, same thing basically, of 1 over n, the integral over b tilde of an x dpx. This is less than 0, but less than lambda times the measure of b tilde. So this is literally the same thing, except you see, we instead of taking a, we take a minus lambda, some a tilde, a minus lambda. So we just get this. And of course, we're going to prove it, we're going to use it in this form. Okay, so now we're ready to finish the proof. So first of all, the case 1 is literally the Birkhoff theorem. So we assume that A is additive, not just subadditive. So this is literally Birkhoff. And then we're going to use that to prove the subadditive case. So here's what we need to do. For alpha less than beta, we take the set where the limit is less than alpha and the lim sup is bigger than beta. So it's x such that the limit of an divided by n is less than alpha, less than beta, less than the lim sup. Okay. And so what we want to show is that the probability or the measure of E alpha beta is 0. So that would be enough, because if you do it for every alpha and beta, it means that the only option is that the limit and the lim sup are the same almost surely, which would be the same as saying that the limit exists almost surely, which is the hard part. Okay, and the trick now is to apply the corollary. Okay. So first of all, we note the following, that E alpha beta is invariant up to measure 0. So why is E alpha beta invariant up to measure 0? That's exactly right. So the lim inf and the lim sup we proved before they're invariant. So everything which is defined in terms of them is also invariant. And so in fact, the trick is, if we are going to restrict our set, so suppose that this set E alpha beta has positive measure, then we're going to restrict the dynamics just to that set because it's invariant. So we can just do that. So if the measure of E alpha beta is positive, then consider T restricted to E alpha beta, right? So from E alpha beta to itself, well, this is also measure preserving system. The same measure, you just restrict the measure. And we're going to apply the corollary to this system. Okay. And so the corollary says the following. It says that the limit as n goes to infinity of 1 over n, the integral over E alpha beta of a n x dpx is less or equal than alpha times the probability of E alpha beta. So why is that? Well, because again, so here we're assuming that the lim-inf is less than lambda. So here we're assuming the lim-inf is less than alpha. So it's the same thing. So and yeah. And however, the other thing we know is that by additivity, so since this is not just subadditive but additive, you take the integral of the nth function divided by n. This is the same as the integral of the first function. So this is literally the same. So this is equal to the I mean, there's no limit. It's just the integral over E alpha beta of A1 x dpx. Okay. And so we want to say that this is less or equal than alpha PE alpha beta. On the other hand, we can do the same thing with minus alpha. So by additivity, we can apply to minus a. So instead of doing the same thing for a, we do it with negative a. And if we do it for negative a, we get the following. We get that minus the integral over E alpha beta of A1x dpx is less or equal than minus beta, the probability of E alpha beta. So now we're done. Because you see, if you swap the signs, this means that the integral is bigger than beta times P. And this says that the integral is smaller than alpha times P. Well, we chose alpha less than beta. Of course, this cannot happen if P is bigger than 0. Right. So if you compare this and this, you compare, you're gonna get that P E beta is 0. So this shows at least the additive case. So literally the idea is we have this nice maximal inequality that shows you that the integral of the average over the set where the limit is less than some constant is bounded by the constant times the measure of that set. And then we do it, we apply it for a lower bound and an upper bound. So for the limit and the lim sup, and we apply it twice, and it gets both bounds, and then these both bounds are incompatible. Any questions? Yeah. Oh, the corollary. Yeah, the corollary is just that we say A tilde and X is defined as A and X minus lambda. Yeah, it's still subadditive, right? Because, yeah. Minus n lambda, yeah. And then the average is, yeah, the average of this is the average of that minus lambda. Yeah, no, it makes sense. Other questions? So the good thing is we're almost at the end of the proof. So now we can do the subadditive version. Okay, so the case 2 is the general subadditive case. Okay, and so the way we look at this, we also reduce somehow to the additive one. So we construct another co-cycle V and X, which is sort of the failure of additivity. Is the difference between A and X and the sum of A1 Tix for I equals 0 to n minus 1. And what do we know about you see, what do we know about the sign of this co-cycle now? Well, by subadditivity, we know that this is less than blah, 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 the sum. So this is always non-positive. And we also compare with the purely additive one, which we call A tilde. And the purely additive one is literally just the sum. Okay. Okay, so this one is additive. So this one, we know we can apply case 1. Okay. So what do we want to show? We want to show that the limit as n goes to infinity of Vn over n of x exists. So why is it enough? Well, of course, because we know that the limit of this one divided by n exists because it's additive. So if we prove that this one exists, then this limit also exists. So this is equivalent. But the good thing is this is negative, so that helps. Okay, so similarly to before, we consider the following two functions. We consider gx as the limit of 1 over n Vn of x, and fx is the Lemma sup 1 over n Vn of x. Okay, and then what do we want? We want for each alpha, we want the set B to be the set of X, such that the difference between the lim sup and the lim inf is bigger than alpha. As usual, we want to do the same thing. So what do we want to show? We want to show that the probability of B is 0. If we have that, that's enough. Okay, so okay, so what do we need? So what do we want here? Okay, so for Feketti's lemma, so remember that we can take the integral, right? We can take the integral of this and divide it by n. So this is a subadditive co-cycle. So if we integrate, we get a sequence of numbers that is subadditive, right? So by Feketti's lemma, if you take the sequence of numbers that is subadditive, you divide by n, and the limit exists. So the limit as this, is equal to the infimum. Could be negative, it could be negative infinity, but it exists. Yeah, we're integrating with respect to x over this measure space. Yeah, everything is, exactly, right? Everything is defined as a function of this measure space x with the probability p. So let's call it that. Yeah. Okay. And so now we do a similar trick to the Feketti's trick, which is also doing a division, Euclidean division. So given epsilon, we pick m such that for m bigger than m, what do we have? We have 1 over m, the integral of Vm, is bigger than gamma. Yeah, gamma is this guy, plus epsilon. I mean, this is just the definition of limit or an inf. Okay, so the real trick is here, we look at the co-cycle not for one step, but at m steps at a time. So we define what a G big M of x, which is the same lim inf, but we just do it at n times m steps. So m is this big number. We just consider the same co-cycle, but doing m steps at a time. And the same is true for f. F is the limb soup of the same thing. Okay? So clearly, what do we have here? We have that by definition, we have that gm, which is the lim-inf on a smaller sequence, is bigger than g, which is the lim-inf on the whole sequence. And symmetrically, we have that fm, which is the limb soup on a smaller sequence, is less than f, which is the limb soup on the whole sequence. Okay. But the claim is that indeed they are the same once again. So the claim is indeed that fm equals f and gm equals g almost surely. Okay, and the proof is once again using some algorithmic, some Euclidean division. So again, for 0 from k between 0 and m, we have v n plus 1 m of x less or equal than v n m plus k x plus v m minus k t n m plus k of x, the usual subadditivity. And okay, the good thing is this is negative, so we can just forget terms. So this is less than vnm plus k of x. And in fact, we can even forget the last k. So this is even less than vnm of x, because this is negative cocycle. Okay, and so now from here we get the invariance. So we get fm of x, which is the limb soup over n of vn plus 1 m divided by n plus 1 m. And this is less or equal than limb soup over n and k of vn m plus k over n m plus k, which is f. And this is still also less or equal than the limb soup over just n of vn m over n m, which is again fm. Yeah, so this is at n, steps by m. This is steps with size m, and this is just every intermediate step. So every intermediate step can be sandwiched between them. So the limb soup is the same. And so similarly, you can do the lim-inf. Gm equals g almost. Okay, almost there. Okay, almost there. So we define a new cycle. Sorry, it's just a lot of like v and m like that. I know it's a bit annoying. So this is v and m, which we had before, minus again some difference, some additive term. And this one, again, for the same reason, is also negative. So again, we subtract from V and M this additive sum. Okay. And so what do we have? So we're almost there. So F minus G is Fm minus Gm, because this we proved. And this is the lim sup of V and M over Nm minus the lim inf of V and M over Nm. Okay, and also this is negative, so this is less or equal than minus the lim inf over N of V and M over Nm. Okay, so before we define the set B, which is the set of X such that F is bigger than G, the difference is bigger than alpha, and this is less than the set where the lim inf 1 over N at this new cocycle V and M less than minus M alpha, and we call this set E. Okay, so what's going on here? So here we say that if this is bigger than alpha, then this has to be bigger than alpha. So otherwise said, so if you unravel the whole definitions, you see that it has to be that this has to be less than M alpha. Okay, and so I think we're basically done. Now we just apply for the last time the inequality, but for this cocycle. So we take this guy and we divide by N. So we integrate. So we get that 1 over N, the integral of V and M dp is what? Is 1 over N, the integral over V and M, again dp, minus 1 over N, the integral of the sum of Vm Pi mx, summing over I. This is less than 0. Okay, so now we take the limit as n goes to infinity of this thing here. So this one is this, yeah, this limit we called gamma before. So we say that they say that the limit as n goes to infinity of 1 over n, the integral of V and M dp is equal to m gamma, because here we divide by nm and we multiply by m. So we have gamma if we divide by m, and we still have m, minus, and this again is additive. So this just converges to the integral of Vm. And this is less or equal to 0. Okay, and the way we chose M a long time ago, what does it? It also shows that this, which is this thing here, yeah, is not just less than 0, but is bigger or equal than minus M epsilon, because we choose the M using Feketti's lemma, taking 1 over M, the integral of Vm. So we are off by epsilon. Okay? So now we apply the maximal inequality. And what do we say? We say that the limit as 1 over n, the integral over this set E, which is where the limit of the average is less than 0, or is less than, yeah, is less than minus m alpha. Well, this is less than minus m alpha probability of E. This is a maximal inequality. So this is negative. So if we integrate over the whole space, this is only going to get smaller. And then this one we just showed that it's bigger than minus m epsilon. So this is bigger than minus m epsilon. So finally, we are done. I know it's a very long proof full of computation. This is probably the most technical proof in this course. Almost. So you see, let's see what we prove. We prove that P F P E times m alpha is less or equal than m epsilon. Right. So then we just obviously remove m and we divide by alpha. So yeah, it's pretty long and it has many steps. So this tends to 0. And so finally, fortunately, after 2 hours, we are done. So the good news is that the proof is over and there will not be other technical proofs of this level of like just sort of just pure analysis. So yeah, so the good news is now we have this nice ergodic theorem that we can use. And in fact, it's pretty strong. So that's maybe one of the reasons why the proof is hard, because it's quite powerful theorem. Okay, are there any questions or comments? Yeah.
So like Vn like is taken by the subtract of the additive part from An.
Yeah.
And then like why there's still like some additive part?
Right, because here we're summing over m terms, not.
It's like you take m stuff, you will get some extra additive like part.
Yeah, exactly. Yeah, so you have to do it twice. It's a bit annoying, but at least once you know how to do it once, then you do it again. Yeah, I mean, of course, again, one common theme is you take m steps at a time, and this helps because you're averaging over the subsequences, and somehow things are more likely to converge if you average along a further subsequence. So this is also a common theme. But other than that, I recognize this is just really really a hardcore analysis proof. So not sure what the moral of the story is. Yeah. Good. Are there other questions or comments? Otherwise, I'll see you again on Thursday.